Hi all, welcome back to Psychophilics YouTube channel. So in today's video we are going to talk about the ways in which knowledge is represented in the machine. Sounds fun? Of course it does. This topic plunges into the emerging field of artificial intelligence. So let's begin with a comparison between humans and machines. Programming languages are used to insert logic in a machine for it to understand input and produce an output. In humans, even if we are given an information which is wrong, we use background knowledge. But for machines, there is no background knowledge. Machines depend on logic for knowledge representation. So let's look at three logical ways of doing it. The first one is going to be propositional logic. So PL is the simplest form of logic where all the statements are made by propositions. A proposition is a declarative statement which is either true or false. It is a technique of knowledge representation in a logical and mathematical form. So for instance, the sun revolves around the earth. This is a false statement, right? Next comes the symbolic logic. Symbolic AI algorithms work by processing symbols which represent objects or concepts in the world and their relationships. The main approach in symbolic AI is to use logic-based programming where rules and axioms are used to make inferences and deductions. Example, and, not, inclusive or exclusive or. Now let's look at the final logic which is the most relevant and most commonly found amongst all programming languages, which is called first order logic. So to talk about that, we are going to look at models of FOL. Let's first recollect the usage of the term model. We use the term model in place of possible world. The models of a language are the formal structures that constitute the possible worlds under consideration. Each model links the vocabulary of the logical sentences to elements of the possible world so that the truth of any sentence can be determined. Models can be thought of as a mathematical abstraction which include the truth or the falsehood of each and every sentence. For instance, if a sentence A is true in a model X, then model X satisfies A or X is a model of A. Understood? Now let's proceed into the domain of a model. The domain of a model is a set of objects or domain elements it contains. The domain is required to be non-empty. Every possible world must contain at least one object. To give you all a heads up, a model in the first order logic consists of a set of objects and an interpretation that maps constant symbols to objects, predicate symbols to relations on those objects, and function symbols to functions on those objects. In FOL, we indulge in what is called as intended interpretation, where it contains the interpretations of all predicates, constants, and functions and objects within that given domain. Let's now talk about syntax. Syntax of FOL refers to properly arranged symbols. The basic syntactic elements of first order logic are the symbols that stand for objects, relations, and functions. Three kinds of symbols include constant symbols, which stands for objects, predicate symbols, which stand for relations, and function symbols, which stand for functions. Each model includes an interpretation that specifies exactly which objects, relations, and functions are referred to by the constant, predicate, and function symbols. Too much theory? Now let's look at an example. For instance, if I type brothers and in brackets Raj, Ravi in, then I'm depicting the fact that brother is a function and Raj and Ravi are terms, basically nouns. We will further understand this in the upcoming section. Now let's talk about the basic elements of syntax in FOL. There are 7. You have constant, variables, predicates, functions, connectives, equality, and quantifiers. Let's go one by one. Let's first talk about constant. A term is a logical expression that refers to an object. Constant symbols are therefore terms, but it is not always convenient to have a distinct symbol to name every object. Constant symbols includes numbers, alphabets, and any name that basically denotes a noun. There are different types of constants. First one is going to be an object constant used to name a specific element of a universe of discourse. Function constants used to designate members of the universe of discourse. Relation constant used to name a relation of the universe discourse. Let's now talk about variables, which is the second element. These include any alphabets which could be used as substitute for the noun. The usage of variables denotes the fact that the noun can have varied functions. A variable is any sequence of lowercase alphabet and numeric character in which the first character is a lowercase alphabet. The quantifiers interact with variables which appears in a suitable way. We will discuss quantifiers in the upcoming sections. Until then, let's look at the two types of variables in FOL which are given below. First one is free variable. A variable is said to be a free variable in a formula if it occurs outside the scope of a quantifier. Second one is a bound variable. A variable is said to be a bound variable in a formula if it occurs within the scope of the quantifier. Confused? You will get it clarified if you look through the video and wait till quantifier pops up. Now let's go to the third element, which is predicates. Predicate in programming language is a statement that contains variables and it gives us a Boolean answer of true or false. In FOL, we usually try to denote unary relation, where n is any relation that can be expressed as mother of or sister of. That is, the predicate of the sentence can only refer to a single subject. For example, I say P and in brackets x comma y. Here, X is term 1, which is name of a student, and Y is term 2, which is name of a university, and P is the predicate. This can be true or false. So P in brackets x comma y. So X may be a student of Y or X may not be a student in Y. So these are the two possible explanations that you can get, right? So if X is a student of Y, then it becomes true. If X is not a student of Y, then it is false. Now let's go to the fourth element, which is basically functions. Simply put, it is associations between objects. Functions can be assigned any number of arguments, but we have to understand that each function will have a fixed set of arguments. So for instance, we take the above example, student of Y. This will return the function to determine if the student is of Y or not. Clear? Confused? Watch it again. Let's go to the next element, which is basically connectives. Connectives are used to combine atomic sentences into the complex sentences of FOL. The connectives include all those used in propositional logic and two new ones which are called as the quantifiers. So you have the following which are being displayed on the screen. You have negation, conjunction, disjunction, implication, equivalence, exclusive, and then you have universal quantification and existential quantification. So we will look into universal and existential quantification further under the topics of quantifiers. Now let's go to the next element, which is basically equality. It is a special type of predicate which indicates if two objects are equal in a domain or not. Equality symbol, which is basically equalizer, is a logical constant and can be best understood as the identity relation. The usage of equality makes the FOL domain stronger in terms of its logical applicability in the domain. The equality predicate can only be used for objects. Remember this. Another symbol is a biconditional, which is used to check if the propositions of two subjects or objects are equal. So remember the difference of an equalizer and a biconditional. Alright. Now let's go to the next element, which is basically quantifiers. The most awaited one. Yeah? So the inclusion of quantifier in FOL is a major difference when compared to propositional logic, and hence FOL becomes more expressive in terms of its logic. In propositional logic, it talks about the facts whether the statement is true or false, right? In FOL, assumes the world contains facts and objects with certain relationships between the objects. A quantifier is a language element which generates quantification, and quantification specifies the quantity of specimens in the universe of discourse. These are the symbols that permit to determine or identify the range and scope of the variable in the logical expression. There are two main types of quantifier, basically universal and existential. Further, we will also look into nested quantifier. Fine. Now let's begin with universal quantifier. Universal quantifier is a symbol of logical representation, which specifies that the statement within its range is true for everything or every instance of a particular thing. The universal quantifier is represented by a symbol of inverted A. Okay, so note, in universal quantifiers, we use the implication sign. Why? That we'll be covering at the end of the video, and if you really get the answer, do comment. If x is a variable and then I write as inverted a and then x, it can be read as for all x, for each x, for every x. Under universal quantifiers, we have another type of interpretation called as an extended interpretation. So earlier we studied about intended and unintended interpretation, right? Both of which were specific to one particular domain. So to understand extended interpretation, let us take one example. So here I have written inverted a and cricketer, which implies person in brackets also x. So this statement says that every cricketer is a person. So for this statement to be true, the cricketer should be a person in all possible extended interpretations that we could make from the statement. Note. Be careful not to use conjunction instead of implication while deriving extended interpretations from a universal quantifier. Both of them have a different meaning. In terms of extended interpretations, we are trying to look for all possibilities from a statement. We are not trying to look for similarities. So please be careful when you are using the symbols. Now let's look into the second category of quantifier, which is basically existential quantifier. Universal quantification makes statements about every object. Similarly, we can make a statement about some object in the universe without naming it by using an existential quantifier. Existential quantifiers are the type of quantifiers which express that the statement within its scope is true for at least one instance of something. It is denoted by the logical operator of inverted E. When it is used with a predicate variable, then it is called as an existential quantifier. In existential quantifier, we always use and or conjunction symbol. Okay, so if x is a variable, then existential quantifier will be inverted ex or inverted e and x within brackets, and it will be read as there exists a x for some x for at least one x. Got it? Now that we have understood the universal and existential quantifier, let's look at a different type of quantifier which is called as a nested. To express complex statements, we need to use multiple quantifiers. The most commonly found is that of a consecutive similar quantifier. For example, I say the statement that inverted ax and inverted ay brother bracket x comma y implies sibling bracket x comma y. This statement tries to denote the fact that x and y are brothers and brothers are siblings. So we do encounter statements with a mixture of quantifiers, not like the one we discussed now. So for instance, consider these two statements. In other cases, we will have mixtures like everybody loves somebody. Means that for every person there is someone that loves. On the other hand, there is someone who's loved by everyone. Do you guys want to try out to write these statements with all the symbols we know? Yeah, you guys did? Now look at the screen. This is the right way of writing it. So the order of quantification is therefore very, very important. It becomes clearer if we insert parentheses. Remember that. So if you look at the second statement, that everyone has a particular property, namely the property that they love someone. On the other hand, the first statement says that someone in the world has a particular property, namely the property of being loved by everybody. So you got the difference between both these statements? Yeah? If not, watch the video again. Now let us look at the connection between universal quantifier, which is basically inverted A, and existential quantifier, which is basically inverted E. The two are interlinked through negation. For instance, if we say all like, the equivalent found would be no one would not like. So to simplify the usage of inverted A and inverted E in a sentence, we can use few symbols. Now that we have understood universal and existential quantifier, let's look at a different type of quantifier called as the nested quantifier. To express complex sentences, we may need to use multiple quantifiers. The most commonly found is that of a consecutive similar quantifier. For example, look at the statement on screen. This statement tries to denote the fact that x and y are brothers and brothers are siblings. We do encounter statements with a mixture of quantifiers. So for instance, consider these two statements. Everybody loves somebody. There is someone who's loved by everyone. Now look at the statements given on the screen. So you do understand the order of quantification is therefore very important, right? It becomes clearer if we insert parentheses. So if you see the first statement, it says that everyone has a particular property, namely the property that they love someone. On the other hand, the second statement says that someone in the world has a particular property, namely the property of being loved by everybody. Now let us look at between the connection of universal quantifier, which is inverted A, and existential quantifier, which is basically inverted E. These two are linked through negation. So for instance, if we say all like something, the equivalent found would be no one would not like something, right? So to simplify the usage of inverted A and inverted E in a sentence, we can use few symbols like logical conjunction, logical disjunction, not or no one, and implication, right? Now let's look into the second part apart from syntax, like so much in syntax. Right, now let's go to the next part of semantics, which is basically the meaning of a well-formed syntax, like an associating meaning. And the third part is basically pragmatics, like how to specify a meaningful expression, like how to use it. Like for example, I want to denote someone is behind you. So how do I do with all these symbols? That is the third part. So before we go there, let's look at the types of sentences. There's atomic sentences or atoms, and then there's complex sentences. Atomic sentences are the most basic sentences of FOL. These sentences are formed from a predicate symbol followed by a parenthesis with a sequence in terms. We can represent atomic sentences as predicate and in brackets term 1, comma, term 2, comma, till term n. So for instance, friends, and in bracket I put C, comma, D. It means that C and D are friends. Very simple. An atomic sentence is true in a given model. The relation referred to by the predicate symbols holds among the objects referred to by the arguments. Please be sure that atomic sentence is not going to have any complex quantifiers or anything. The second part of a sentence is going to be complex sentences. So complex sentences are made by combining atomic sentences using connectives. So consider the statement. X is an integer. It consists of two parts. The first part is the X. It is the subject of the statement. And second part is an integer. Is known as a predicate. So now I hope you understand the two types of sentences. I hope you did, because we are going to do something really fun right now. We are going to do an activity. Now let us try to replicate a few sentences, okay? Here are 5 sentences on screen. First one is all birds fly. Every man respects his parents. Some boys play cricket. Not all students like both mathematics and science. Wow, this sounds complicated. Only one student failed in mathematics. So let's start doing these sentences into equations, maybe. Yeah. So let's go with the first one. All birds fly. It's very simple. For all, I use a universal quantifier, which is basically inverted A, and I put bird, and I will denote a variable in brackets, which is X, and I'll put an implication symbol fly, and I'll put the bracket X, which basically means all birds fly. Now let's do some boys play cricket. So here what I'm going to do, I'm going to use the not symbol. Is that so? Am I right? No. I will be using the existential quantifier here, which says some boys play cricket, and I will follow the same format. Now let us do one more question. Only one student failed in mathematics. So here what I'm going to do is I will be using the existential quantifier again. Those who guessed, you guys are right. And I'm going to put the not symbol for saying that not every student has failed. Only one person has failed. Right? Now, the rest 2 questions are up to you guys to try it out. And if you guys have tried it out, put a pause. And once you're done, play the video again, because the answers are showing up now. So these are the answers. I hope you guys had a fun time watching this video. And I really hope you guys were able to get more clarity on this topic of FOL. If you really like our video and you want more and more videos explaining topics in AI, please do like, share and subscribe to our channel, Psychophilics. And we're really glad we could help you guys in all ways, and thank you so much.